ಮ್ಯಾಪಿಂಗ್ ಆಗಿದೆ ಅಲ್ಲ, ಮತ್ತೆ ಮ್ಯಾಪಿಂಗ್ ಮಾಡೋದು ಕಳ್ಸರ್ ನಿಮಗೆ ನಿನ್ನೆ ನೋಡಿ ಸಬ್ಜೆಕ್ಟ್ ಮ್ಯಾಪಿಂಗ್ ಅಂತ
ಆಲೋಚನೆಗೆ ಇರ್ಬೇಕು
ಆಗಿದೆ ಅಲ್ಲ ಮ್ಯಾಪಿಂಗ್ ಎಲ್ಲ ಅಲ್ಲ ಈಗ ನೋಡ್ರಿ ಈಗ
ಅಪ್ಡೇಟ್ ನಂಬರ್ ಆಫ್ ಟೈಮ್ಸ್ ಅದನ್ನ ಅಪ್ಡೇಟ್ ಮಾಡ್ಬೇಕು. ಒಂದೊಂದು ಜಾಸ್ತಿ ಮಾಡ್ಕೊಂತ ಹೋದ್ರೆ
ಅಪ್ಡೇಟ್ ಅಲ್ಲ, ಮ್ಯಾಪಿಂಗ್ ಆರ ಮುಗಿತು, ಅಪ್ಡೇಟ್ ಏನ್ ಲೆಕ್ಕಿಲ್ಲ ಅದು 18 ಇಸಿ.
ಹಾ ಸರ್, ಅದು ಅಪ್ಡೇಟ್ ಇಂದ ಫ್ಯಾಕಲ್ಟಿ ಮಾಡ್ಬೇಕು ಅಂತ ಹೇಳಿದ್ರೆ ಅವ್ರವ್ರು ಎಷ್ಟು ತಗೊಂಡಿದ್ದಾರೆ ಅಂತ
ಮಾಡ್ಕಂತಾರ ಬಿಡ್ರಿ, ಏನ್ ಗೊತ್ತಿರಲ್ಲ ಅವ್ರಿಗೆ.
ಹೇಳ್ಬೇಕು ಸರ್, ಅದು ಇನ್ಫಾರ್ಮ್ ಗ್ರೂಪಲ್ಲಿ ಅಪ್ಡೇಟ್ ಇವಾಗ ಸಬ್ಜೆಕ್ಟ್ಸ್ ಹಾಕ್ಬೇಕು ಗೊತ್ತಿಲ್ಲ. ನಂಬರ್ ಆಫ್ ಟೈಮ್ ಪಾಸ್ ಅಂತಂದ್ರೆ ಇಲ್ಲ ಒಂದೊಂದು ವರ್ಷ ಇಂಪ್ರೂವ್ ಮಾಡ್ಬೇಕು.
ಎಲ್ಲಪ್ಪ ಮಾಡ್ಕಂತಾರ, ಅದೆಲ್ಲ ನಾವು ಮಾಡಕ
ಯಾಕೆ
ಅಮ್ಮ ನನಗೆ ಹೇಳುತ್ತೆ,
ನಾವೆಲ್ಲ ಹೇಳ್ತೀವಿ, ಇದು ಮಾಡ್ತಾರೆ.
ನಮ್ಮ ಮಗನ ಸಾಧ್ಯ.
ಇಲ್ಲಿ ವಿಡಿಯೋ ಫೋಟೋ ಅಂತ ಭಾಳ ಫೋಟೋ ಇದರಲ್ಲಿ ಎಂಟರಲ್ಲಿ ಸ್ಪೇಸ್ ಕೊಟ್ಟೋದು. ಕ್ಲಾಸ್ ಇದೆಯಾ?
ಕ್ಲಾಸ್ ಮತ್ತೆ ಸುಂಡಿ ಆಯ್ತು. Good morning. Shall we start? Shall we start? Good morning. Shall we start? Good morning, guys. Today I'm a bit late. Sorry for that. Shall we start? Yeah, fine. Okay. In the previous class, we just saw the parts of simulation. the various things associated with the verilog program, the coding, and also I have given an assignment to submit. So if you have not done that assignment, please submit that. Take mark it as important. It will be evaluated for 5 marks for your internals. Okay. Okay. In today's class, we'll just deal with the more practical way of updating the or writing the program. Let us try to see that with the help of a video. So I would rather stress on this point. Watch the videos, try to understand, make a note of those things. So what you watch there, if you have any doubts at the end of the class, you can ask me. Okay, fine. Please watch this video carefully.
Okay, welcome back. In the last video, I showed you how to create a very simple verilog module that described a simple structural circuit. So here is the circuit that we had described using verilog. Now in the last video, we described the circuit and went through the process of synthesis. After synthesis, we want to make sure that the design works as we had intended it to. So this video will show you how to use simulation, create a test bench, and do a simulation on the verilog module that we've just created. Okay, in order to create a simulation source, okay, so in your Vivado project, on the same project, go to Add Sources. Last time we did create design source. This time we're going to do create simulation source. So select simulation source. Hit next. Now we don't have a simulation source already created, so we'll click on this plus sign here, create file. I like to name my simulation source, since they're called test benches, that's the official name. I like to say TB and then the name of the verilog module I'm simulating, and the name of the verilog module was called mycirc. So I created a file name called tb_mycirc.v and keep it local to your project. Okay, so we have the file. Now you can hit finish. Now it says, what are the inputs and outputs for the simulation source? Now, really, for a simulation source, we don't have specific inputs and outputs like the way we had for our real module. Simulation is about energizing these inputs of the real module and observing the output Y. Okay, so our verilog test bench module for a simulation source does not have inputs and outputs. Okay, you can think of the inputs as being things from, let's say, switches or function generator in lab, and the output being something you're observing on the oscilloscope. Okay, so the test bench module, which is going to energize my circuit, does not need its own independent input and output. So we'll skip this. It says, are you sure you wanted to use these values? Yes. So we should be seeing a simulation source right here called test bench mycirc. So let's open that. It created a module which is fairly empty right now, has no inputs and outputs. Okay. Now, when we do the simulation, we'll go through a few things, and here's an example. All right, so here is a file available on Blackboard called an anatomy of test bench. For a test bench, that's the name of the module. We have no input output. Okay. The inputs of the main source are declared as registers. These are declared as registers because we want to hold the value at the inputs until we change it. The outputs are declared as wires. If anything changes, we want to observe that right away. So we don't want to hold on to the old value. We want the output to change as soon as something changes. So those are declared as wires. Okay. So in our module here on the test bench, we're going to declare the inputs of the original module as reg. Okay, so we're going to declare reg A, reg B, reg C, and reg D. Those were the four, A, B, C, and D were the four inputs in the previous module that we want to test. We want to declare our output as a wire. So we have wire. The output was called a Y. So we have Y. Okay. All right. So now what we want to do is called instantiating the module. Instantiating a module, if you want to think about it in terms of programming, C programming or Java programming, instantiating a module is somewhat similar to what you would do when you call a function that you've created in programming, software programming, right? So instantiating a module is basically putting the module together. Actually, we've done this. This is instantiating the AND module from an internal library. Okay. In our case, we're going to instantiate the module here. Our module name, so when you instantiate the module, you have our module name. My module name is called my circ, right? Just like how we instantiated the AND gate, now we're instantiating this guy, my circ. Okay. What do we expect? We expect the output first, because that's how we had initially created this, with the output first. So you can say Y, comma. Next, we expect the input that's on A, so A, B, C, D. A, B, C, D. Okay. That's how you instantiate the module. So, oh, I forgot to give the module a name, which was, that was the name of the module, and this is what we called AND gate on our schematic. Similarly, we will call our unit, let's say unit under test, UUT. Okay. You can call it whatever name you want. It's a unique name given to that module. So my circ is the name of the module. That's the name of the module on the schematic, I guess. And that's the ordering of the input and output that we have. Okay, so module instantiation. So okay. Now we want to exercise the inputs and outputs and observe inputs to this module and observe what happens. So
great. So I hope everyone is come back ready.
Right, so let's add the stimulus. And to add the stimulus, we'll use the phrase initial, begin, begin and ends are like curly braces in other programming. So let's call A equals 0, B equals 0, C equals 0, and D equals 0. And then we'll let these inputs stay like these for 100 nanoseconds. That's what that means. After that, let's say we want to change all of this. So we have applied 0, 0, 0, 0. Let's apply 0, 0, 0, 1. 0, 0, 1, 0. One, 0, 0, 0, 1, 1. And we could keep going like this until we, if it's a small circuit, we can exercise, in this case, there's only 16 possibilities. We could exercise all 16 possibilities. If it's a larger circuit, we could exercise just a subset. Let's say, for example, A equals 1, B equals 0, C equals 1, and D equals 1 for 100 nanoseconds as well. So once the test bench, so we've created the stimulus, and these are the inputs assigned to ABCD, values assigned to inputs ABCD, and they should result in an output on Y. So once we're done, hit save. So save this, right? As soon as you save this, now notice under sim1, what happened? The test bench MyCirc, since it instantiated this particular module we had created and called it UUT, showed up as UUT, and it's linked to that verilog file. Okay. Right. Now let's hit run simulation. we want to do a behavioral simulation. So let's do a behavioral simulation. It's executing the analysis. This might take a little bit of time depending on how large your test bench is and how big the circuit is. So give it a second. And here you go. So it's completed. It has completed the simulation process. So let's go take a look at the results that we got right here on the waveform. This waveform, you might have to expand some of these windows a little bit. You don't see everything here, so right click on the window and say full view. This will show you everything. So let's take a look. And just like how you use Xilinx ISC, this one has similar cursors you can place at different locations. This yellow thing is a cursor. If I place it right there at 49 nanosecond, these are the values 0, 0, 0, 0, and the output is 1. The next one 0, 0, 0, 0, 0, 1, the output is a 0. Now let's go back to and make sure that the circuit, okay. All right, here it is. 0. So initial stimulus is 0, 0, 0, 0. So 0 and 0 on A and B gives you a 0 on T1. A 0 on C gives you a 1 on T2. So 0 or 1, T3 is a 1. D was a 0, so T4 is a 0. So Y should be a 1. Is that what we see? For 0, 0, 0, output Y is a 1. Now let's see what happens when 0, 0, 0, 1 is applied. So 0, 0, 0, 1 is applied. So everything else was 0, 0, 0 just as before. So T3 was a 1. 1 and 1 results in T4 being a 1, which changes Y to a 0. And that's what we see here. And you can verify that this waveform actually proves that the verilog module we described here is doing the exact same functionality as the original schematic we came up with. Now this simulation step is crucial because it lets us gain confidence before we build larger modules using MyCirc.v.
Okay, guys.
Hi, today I want to show you how to use models.
Okay, guys. Hope you got the glimpse of glimpse of programming in Verilog. Okay. So now let us try to discuss the next topic, that is levels of abstraction. So as I mentioned, there are 4 levels. In the previous class, we have discussed this concept. There are 4 levels of abstraction. First one is behavior level. This is the highest level of abstraction provided by the Verilog. A module can be implemented in terms of desired design algorithm without the concern of the hardware implementation. We may not know the exact hardware required for designing the circuits. If you know the behavior, we can write the program very long. That is the first level. It is the easiest level. So behavioral algorithmic level, we call it as without the concern of hardware, we can design a circuit. Second one, designing at this level is very similar to C programming. So it is very similar to C programming. Any particular person having a little knowledge of electronics can also design circuits in this type of abstraction. Second is data flow level. At this level, you can one can look at the circuit and the specifications are returned by specifying the data flow. Here, the designer is aware of how data flows between hardware registers and how the data is processed. So you need to have the information about data flow. Then only you can write this type of program. So that is the second level. So somewhat sophisticated from the first level. Third is gate level. The gate level, the model is implemented in terms of logic gates. I'll just share the slide once. Wait one second. Okay. A Chrome tab. Google. Okay, fine. Yeah, you can see here the levels of abstraction. First one is behavioral or algorithmic level. The second is the data flow level. The third is the gate level. The model is implemented in terms of logic gates and interconnections between these gates. So gate level, okay, you can write if you have the precise logic diagram of the circuit, then only you can write this type of programs. So the complexity is more as compared to the other two types. The last type is switch level, which is the lowest level of abstraction. This is the lowest level of abstraction provided by Verilog. This is the lowest level of abstraction provided by Verilog. A module can be implemented in terms of switches, storage nodes, and the interconnections between them. So this is the complex level of programming. Design at this level requires knowledge of switch level implementation details. So transistor level, we need to have the information. Then only we can go with the switch level type of abstraction. So there are four types of or four methods of writing a program. So that we call it as level of abstraction. The first level is behavior level. Repeat with me. First one is behavior level. The second one is data flow level. The third one is gate level, and the fourth one is switch level. So gate level is also called a structural level programming. Next, flexibility of abstraction levels. The higher the levels of abstraction, the more flexible and technology independent design. So the first behavior level is the easiest way. So it is a higher level of abstraction. The design is more flexible and it is technology independent. So technology independent. I need not bother about the hardware used. As one goes lower towards switch level design, the design becomes technology dependent and inflexible. That is why we cannot go with or we cannot always try to design in the last level. First, as a programmer or the beginner, we'll try to design the things with the help of behavioral level or data flow level. Example, the analogy of C programming with assembly language programming. It is easier to program in a higher level language. Definitely in C you can easily program, whereas in case of assembly language you need to remember the mnemonics or you need to remember the specific instruction set and then you can execute the programs. Fine, that is the meaning of this. So this I have covered in the previous class, instance and instantiation. Example, I have taken example of T flip-flop and how this D flip-flop is used. And a module inside a module cannot be called. You cannot call a module inside a module. Once you say it is a module, end module, then only you can write the another module. So module, module name, module terminal list, module internals, end module. Then only we can try to write the we can write the program correctly. You cannot nest the modules. It is not important not to confuse module definitions and instance by module. So important. So you cannot confuse module with the instances. Instances are created by the module itself. Module will invoke an instance. So in the previous class I have dealt with the instances. I will not take much time on that. Example of illegal module listing. So you can see here. Can we do like this, sir? No, it is not, because module ripple carry counter. So you can see here it is module ripple carry counter input reset. So once again a module is written here. So it is illegal module nesting. You should not use this type of statements, because module name, module input terminal list, then the module internals, then end module. So you cannot nest. Once nesting is not allowed in Verilog. You cannot force one module inside the another module. Got it? Hello? Are you able to understand? Hello? Yeah, fine. You cannot nest the modules inside the module. Module inside module is not allowed. Then you can see that components of a simulation or parts of a simulation. Applying stimulus or writing a test bench would be covered later, definitely. At this point, I feel that it is difficult to write the test bench code for you guys. Just understand that we need to write a test bench code for applying the inputs. As you apply the input from the logic kit in your lab, ನಿಮ್ಮ LD ಲ್ಯಾಬ್ ನೆನ್ಪಡ್ಕೊಳ್ಳಿ. LD ಲ್ಯಾಬ್ ಅಲ್ಲಿ ಯು ಆರ್ ಪ್ರೊವೈಡಿಂಗ್ ದಿ ಇನ್ಪುಟ್ಸ್ ವಿತ್ ಹೆಲ್ಪ್ ಆಫ್ ಎ ಲಾಜಿಕ್ ಕಿಟ್ಸ್. VCC ಕೊಡ್ತಾ ಇದ್ರಿ, ಗ್ರೌಂಡ್ ಕೊಡ್ತಾ ಇದ್ರಿ, ಮತ್ತೆ ಇನ್ಪುಟ್ಸ್ ಕೊಡ್ತಾ ಇದ್ರಿ. ಸೊ ಇಲ್ಲಿ ಏನಾಗುತ್ತೆ, you need to write one more code that is called as test bench code. At this point, it is not. I personally feel that it is tough to you guys. In the later class, I'll cover you. I'll show you how to write test bench code. So next we'll go the next module, basic concepts. So the topic learning objectives, TLOs, are understand lexical conventions of operators. For operators, comments, white spaces, numbers, strings, and identifiers. So how to write a program using these things. Define the logic value set and data types such as nets, registers, vectors, numbers, simulation type, arrays, parameters, memories, and strings. Identify useful system tasks. Learn basic compiler directives and define macros and include files. So first chapter or first module is covered now. So we'll move to the next module. So lexical conventions in programming, we need to use this lexical convention. So you have to precisely use this and you can write the program. First one is white spaces. White spaces can be written like this: blank spaces, /b, tabs, /t, and new lines /n comprise the white spaces. They appear as white space. They /b, /t, /n comprise the white spaces. So if you give this, what happens to your verilog? Verilog white spaces are ignored by verilog except when it separates tokens. White space is not ignored in strings. In strings, it is accounted, whereas it is ignored in many cases. White space will be ignored. So while typing, you may ask me, sir, space kotre work agata? Yes, kota. Space kotre work agata? Kodilla work agata. Yavaga, it is ignored. When in normal programming, it is ignored. When it is inside a string, it is accounted. Hello world, hello space world, then it will be considered. In string, it will be considered, whereas in all the programmings, white spaces are ignored. White spaces are ignored. Then comments. Can you add a comment? Why comment is required? Not your Facebook comments. ನಾನು ಕಮೆಂಟ್ ಮಾಡಿದ, ಅವ್ರು ಕಮೆಂಟ್ ಮಾಡಿದ್ರು, ಇವ್ರು ಕಮೆಂಟ್ ಮಾಡಿದ್ರು. ಸೆಲ್ಫಿ ಹಾಕ್ತಿರಲ್ಲ ನೀವು, ಹಂಗೆ ಹಿಂಗೆ ಎಲ್ಲ ಮಾಡಿ ಹಾಕ್ತಿರಲ್ಲ, ಸೆಲ್ಫೀಸ್ ಹಾಕ್ತಿರಲ್ಲ. So you will be waiting for comments, right? Oh, nice, wow, cool. A super pic, cameraman, hats off, hangela ಆಗ್ತಿರಲ್ಲ. Comments are very important in writing a program also. Why? Because using the commands, one can understand your program. Programming is done in many ways. A program can be written in many ways. If you wish to make understand the person who is reading the program, so write the comment. Always write the comment lines. Comments can be inserted in the code for readability and documentation. For readability and documentation, we'll go with comments. There are two ways to write comments. A one-line comment starts with double slash. Verilog skips from that point to the end of the line. So Verilog will never consider, but comments are required to understand the code for readability and documentation. So ಏನು ಕೋಡ್ ಬರೆದಿರಾ ಬಿಟ್ಬಿಡ್ತೀರಾ. So comments ಇದ್ರೆ ಗೊತ್ತಾಗುತ್ತೆ ನಮ್ಗೆ ಯಾವ್ದು ಬರೆದಿರಾ ಕೋಡ್, ಏನಕ್ಕೆ ಬರೆದಿರಾ ಅಂತ. So writing comments is mandatory. A multiple comment line starts with slash asterisk and ends with asterisk slash. You can write multiple lines of comment. Multiple line comments cannot be nested. So you cannot nest them. You can end them with the asterisk and backslash. However, one line comments can be embedded in multiple line comments. So while writing the program, we'll come to know. Example of comments. So you can see the statement here. A is equal to B double ampersand C. This is a one line comment. Why? Because backslash I'm using. This is a one line comment. So if you want to write a multiple comments, you can slash asterisk. This is a multiple line comment which can be used to give comments in more than one. Star, so asterisk, backslash. So this is valid. These two are valid comments. So this is an illegal comment. Why? Because you are trying to nest the multiple comments. So this is a legal comment. Why? Because asterisk, no, sorry, slash asterisk. This is double slash a legal comment. Star, asterisk, backslash. So this is a legal comment. So these are the example of comments. Don't confuse with much with this. Comments are only required for comments can be inserted in the code for readability and documentation. Okay. Today I'll stop here. So in today's class we started this next module, that is the second module called as lexical conventions. So here the main key point to be remembered is Verilog HTML programming is easy Only thing is you have to study. Once you come to the regular colleges, we'll start the programming directly. Now the class is open for doubts. You can ask me the doubts. Mark your attendance. And just I'll unmute Sinchana S. Sinchana S, unmute yourself. Hello. Sinchana. Hello. Are you guys able to follow, guys? Are you able to follow, guys? Fine. Sandhya G. Sandhya G. Unmute yourself, Sandhya.
Yes, sir.
Okay, are you able to follow?
Yes, sir.
Okay. Okay, fine. I have solved the assignment. Hope you guys have returned the assignment. Submit it by Thursday. Thursday is a deadline for submission. It will be evaluated for 5 marks. Okay. Okay. If you don't have any doubts, you can leave the class. Thank you very much.